Okay, welcome to part 2 of the video series titled TensorFlow Tutorial for Beginners. In the previous part of this video series, we basically discussed what is TensorFlow, what is Colab, which is a coding environment, not particularly for TensorFlow, but for Python and for other kind of languages as well. But TensorFlow is pre-installed there as other libraries. And you can work in Colab. We also went through terminology, some basic terminology regarding neural networks and convolutional neural networks. In this part, we will be basically implementing a plain neural network for classification. Basically, we will be classifying fashion MNIST data, which has 10 classes. And we will be actually implementing, we will be actually going through the whole TensorFlow module in this particular video. So let's dive in and see what can we do with this TensorFlow. Already we have, that's what we did in the last video, import TensorFlow in Colab, the variant. Let's import a couple of more libraries that are important. Import NumPy as NP, that is required, and import matplotlib .pyplot as plt, just for displaying images. So let's see, yeah, these are also imported. So now what we do is we actually load the fashion MNIST data. So what we do is the following. We write, okay, fashion MNIST data, fashion MNIST data equals to tf.keras. That's Keras is the core library inside this TensorFlow that actually does the most interesting stuff for TensorFlow. Datasets, datasets dot fashion MNIST. So let's say that's FM. And then what we do is we say, okay, train images, and train labels. Let me write this as X train and Y train. That's one thing that we want. And then we have this X test and Y test. These are the labels that we want, and we say, okay, fm dot load data, and this will load this data from the internet, so it may take a while for loading this data. So it is downloading the data for you. Yeah, so I guess the data has been downloaded. So yeah, the data has been downloaded. Let's see the shape of X train and Y train and all that stuff. So for example, X train dot shape, let's display the shape of the data. And the shape is, there are 60,000 images. Each image is 28 by 28. And if you see the shape of Y train, that should be a vector with 60,000 images, 60,000 labels. If we see the unique labels, np.unique ytr, then it should return the unique labels. So the unique labels are 0, 1, 2, 3, 4, 5, 6. So there are 10 classes. Each label, one label is 0, 2, 3. These are the labels. So there are 60,000 examples for 10 classes. Further, we can have these class names. Let's write these class names. So class category names, let's say class names, we can write them as a list. For example, the first name might be t-shirt, that's for t-shirt. And then we can have trousers. Then we have the first label is for t-shirt, the second label is for trouser, the third label is for pullover, and the fourth label is for dress. And the fifth label is for quote. The sixth label is for sandal. And then we have the next label is for shirt. That is something that I know about this data. I mean, if you see the MNIST data, these labels, they correspond to these classes. Sneaker, and then we have bag, and then we have eventually the ankle boot. So ankle boot. So these are the class names. So if we, for example, if we see the YTR, inside that we see, okay, in YTR 19, what is the class name of it? So we can go to CN and just index that, and we will be able to know what is the so it's a quote. So the 19th example basically is a quote. Yeah, so that's about the data set. It has these kind of images. Further, we can have, we can plot these images using this PLT, for example, plt.figure, and we can have plt.imshow xtr training images. Let's say 0th image. Let's just show that. Oh, why you are showing a lot of these things? Xmap this, and then we can have cmap equals plt.cm.bone. I guess that should work. So let's see if it works. Yeah, so that's the image. That's the image. This is the 0th image. We can have another image. We can have another image. By the way, we can see what's the label of this image. What's the label of this image? This is the class name into YTR training and 0. I guess it should be ankle boot. Yes, it is ankle boot. So that's the data set. Now we really want to, we have the test training and test splits. If you're not familiar with what do we mean by training data, what do we mean by test data, I will encourage you to go to our earlier videos on YouTube if you want a quick tutorial for machine learning, or go to AI Sciences for a detailed tutorial about machine learning. Next, what we do is we scale these images. Data scaling is required in most of the cases, and it should be done because it has no harm. So the images are basically the maximum value of the image is 255. So let's scale them from 0 to 1 and do the same with test images. XTST divided by 255.0. So that will do the scalings for us. Yes, the scaling is done. Next, what we do is we basically implement our neural network model. So let's build a model, MODEL model, the neural, or let me call this as neural network model. Neural network model that is basically tf.keras.sequential model. So that's the model, and inside this model we have to specify the architecture of this particular model. So the model basically is tf.keras. So let me just, yeah, so let me, yeah, so tf dot keras dot layers dot flatten, and this first layer, flatten layer, is used because the image is 28 by 28, so we make the image as a long thin vector of 28 square pixels, 28 square values, and the values are received as a vector to the input layer. So this flatten actually does that. Yeah. So flatten. So this. So input shape equals what's the shape of our image? Our image is 28 by 28. So that's our first layer. We basically done this, and then what we do is we add our another layer, tf.keras dot layers dot dense. That's a dense layer. We can now we need to this is the first hidden layer, by the way. Now that we are going to define our first hidden layer, so how many units we really want there? Let's say we want, let's say 100 units. So what will be the activation for each unit? So the activation is activation equals to, let's say, relu, or we can have other activations as well. So that's our first layer. Now we can add a dropout layer if we really want a regularization on this. So tf.keras dot layers dot dropout, and we can have this dropout layer, and here we have to specify the rate of dropout. Let's say 20%. Just randomly remove the 20% in the dropout. So that can be done. Then we can have another layer if we really want. Keras dot layers dense dense, and here we need to specify how many units we want here. Let's say we want 50 units, or maybe I mean any number of 60 units. And activation, here we said the activation is, again, let's say relu. We can change this activation if we want. If you think that we should have a dropout on this layer as well, we can add the dropout factor here. So we just copy this, we paste here below, and that's a dropout. Maybe the dropout here we want as 10% or something else. These are hyperparameters. And then finally we can have tf.keras dot layers dot dense, and we have 10 classes, so that's the final. So our model basically consists of the first hidden layer has 100 units, then we have a 20% dropout rate. The second hidden, so again it has two hidden layers. The second hidden layer has 60 units and it has a 10% dropout rate. And then the final layer, which is the output layer here, has 10 units because we have 10 classes. We will add a softmax layer later on top of this layer to convert these values to probability for each class. But let's see if this model that we have implemented in TF, if it runs properly. Let's see if there is no error. Yeah, there is no error. It runs properly. Now what we do is we basically have to compile this model. So what we do next is our neural network model dot compile. We have to compile this model, and here we have to set certain parameters. If you remember, in the terminology we have optimizer, loss, and these kind of stuff. So what we do is we set the optimizer as Adam. There are other optimizers as well, but for classification problem, it is good to use Adam. It performs well, although nobody can say that the other optimizers are better than this, but maybe practice shows that Adam works fine. We have to specify the loss. Loss is basically tf.keras dot losses dot sparse cross entropy, that mostly people use, and there are parameters like from logit, from logits, and make it true. So that's the loss. Next, we also have to specify metric, what kind of metric we really want for the performance. So the performance metric here we are setting as the accuracy. There are others as well. So accuracy. So that's it. It should work. Let's compile it. If there will be there are problems. Indentation error. Okay, so I guess the indentation should be done properly here. Yeah, again indentation error. Why is that? That's so why don't we just use this and avoid these indentation errors? Yeah, now everything should work perfectly fine. Oh, invalid syntax. Why? Accuracy. Let's see the metric. Sparse cross entropy. Oh, why I have finished this here? Yeah, I shouldn't. Let's run this. Yeah, it runs properly, I guess. Yeah, it runs properly. So there was a parenthesis error. So it runs properly. Now, after having this model compiled, what we have to do is we actually start our training. So what we do is we start training. We said, okay, our neural network model dot fit. What are the training? Where is the training data? It's XTR. What are the training labels? That is YTR. And how many epochs we really want? So epochs equals to, let's say 10 or 20 or something. Let's say 10 epochs. The epoch is the one complete iteration over the data set. Yeah, so let's run this. So it will take some time. That's the first epoch, and that's the second epoch. So these 10 epochs, to complete these 10 epochs, it will take, so that's the training of neural network in TensorFlow that is going on. Yeah, let's see. Yeah, so it is done. The training is done. Now we really want the predictions on the test data, the unseen data. So for that, we add a softmax layer. So let's have a probability model over the last dense layer. Remember, the last dense layer has 10 values. So that converts these 10 values to probability distribution. So our probability model is basically tf dot keras dot sequential, and here we add a model, add our model, neural network model, and then we add another layer, which is the softmax layer, tf dot keras dot layers dot softmax. So this softmax layer is added, and now we have these probability model for that. So remember, this softmax layer actually normalizes all these values to probability distribution. So we do that. Now we have this. Now we can make our predictions. For example, the predictions, the predictions on the test data, that is basically Y prediction is probability model dot predict. And we can predict it on XTST, the test data, and it is making predictions. Now we can see this prediction on the very first test data. That prediction will give us the probability distribution. Basically, it will give us what is the probability for class 0, what is the probability for class 1, what is the probability for class 2, and so on. So let's find out the exact label for the max. So what we do is class label is basically np.argmax, and we have this y y prediction 0. So at the very first test example, what is the class label? So here, if we see the class label is, and if we see the exact class name, we can go to CN, our class names, and we can have this class label, and that class label, our model returns it as ankle boot. So let's see what is the true class label. So ytst 0 CN. So the true class label is also ankle boot for this particular example, and our model all predicted ankle boot as well. Let's go to some other value, prediction value, let's say on 12. So let's go to 12 and do that. Now the class label is sandal. Oh, we have to check for 12. And yeah, so it has confuses the sandal with sneaker. So the actual class was sneaker, and our model predicted as sandal. So let's go to, let's say 100. Let me write this as I equals 100, and we write I here, and we go for this. That's our model. It predicted as dress. So what's the true label? The true label is dress. Okay, so that's how it works. So the basic idea here is to build the model. You can add or drop more layers, add regularization if you really want, using dropout. And once you have a model, you have to further set, you have to compile the model by setting optimizer, loss, and metric. Once done, then you're ready for training. .fit function will train. Number of epochs, more epochs means more training, but be careful, more epochs also means maybe overfitting. There are ways to stop this overfitting using early stopping and other criteria that is discussed in more detailed course in deep neural networks at AI Sciences. But here we have just used the fixed epochs. Once the training is done, your model is trained. Now you can just now you can convert your values to simply probability distribution, and you can predict the likelihood for each class. And then you can pick the max probability as a class label, and that's it. Yeah. So that's it about this video. In the next video, we will be solving the same problem, exactly the same problem, using convolutional neural network. Actually, this is the problem of images. So why are we really flattening out these images at the very first layer? If you see that in the very first layer, we actually flatten the image and just break out all the spatial correlations and structure inside the image. Actually, convolutional neural networks say that spatial structure can be exploitable for performance. And in the next video, we will be actually implementing a convolutional neural network for MNIST fashion dataset. Hope to see you in the next video.